Welcome back, Physical Science 20. This is the last booklet in the FC3 section, and it deals with percentage yield and looking at equations and realizing that we don't always get all of the product that we expect to get. For example, if we look at winemaking and converting sugars into ethanol and carbon dioxide in wine, for example. We used yeast cells in order to cause that conversion to happen. And as the alcohol or ethanol content increases, the yeast cells die and we aren't able to convert all of that sugar into ethanol. And in fact, with wine, around 14% is how much ethanol we get compared to what we theoretically should get. So the idea of a theoretical yield, it's a prediction of how much product we should get based on the stoichiometry of the reaction, what the reaction suggests that we should get. And of course that would assume that 100% of the conversion would happen. But of course in real life that is rarely achieved. We get an actual yield, which is the amount of product that we actually get during the experiment or some industrial process if it's an industry, and it's usually less. So that means that some of the limiting reagent did not completely get converted. And they're very, and as mentioned here, actual yield is never equal to theoretical yield. And the reasons why that doesn't happen is that we could lose some of the reactant in some way, so lose some of it. It could be spilled, or as we're transferring solutions to another vessel, they could have been lost that way. If heating was involved, splattering could have happened, and of course the equipment may not be the greatest, and having too many steps could cause a loss of reactant and therefore not all that being converted into products. So if you could reduce the number of steps, you would get more of that reactant turning into product. And of course, impurities in the substance that we're using. So in the case of sugar here, glucose, it may not be 100% sugar or glucose, therefore obviously all of that sample would not be converted into ethanol. So if we circle this, how percentage yield is determined, you take what you actually get divided by what you should get due to the formula, the equation, and multiply by 100%. So that is a very simple way of calculating that. If we look at this first example here, it says methanol can be made by the synthesis using carbon dioxide and hydrogen, and we can make ethanol there and also water. During an investigation, if I had 20 grams of hydrogen and I had excess carbon dioxide, so enough to make sure all of this hydrogen is converted, I get 102 grams of methanol as a result. What is the percentage yield of this reaction? So we have to be careful here. This 102 isn't the theoretical yield. It isn't the calculated yield from the 20 grams. It is the experimental result. So it represents the actual yield that we obtained when this was actually experimentally performed. So to figure out the percentage yield, I'll have to figure out first of all what should I have got. If I had 20 grams of hydrogen with excess carbon dioxide, what should I have obtained? So if we look at the solution here, we need to go from 20 grams of hydrogen to moles, then use the mole ratio to go from moles of hydrogen to moles of methanol, then lastly figure out the grams of ethanol obtained, because this 102 represents the actual yield. Okay, so rather than doing this in one step, the booklet here chooses to break it down to three separate steps, going from grams to mole to mole using the mole ratio, and then moles to grams over here. And of course, wherever the word amount is used, that actually means moles. So 20 grams to moles for hydrogen. Here's the setup there. We get 9.9010 moles of hydrogen. Then they go from moles of hydrogen to moles of methanol. It's a 3-to-1 ratio. 3 in the bottom, 1 on top. 3.3003 moles of methanol is obtained. And then going into grams, multiplying by the molar mass, and we get 105.78 grams. So as you can see there, I should get 105.78 grams of methanol, but what we actually get is 102.0 grams So that's the big thing. The trickiest part of the question really is distinguishing between the theoretical yield and the actual yield. So actual divided by theoretical, 102 divided by 105.78 times 100, it works out to be 96.4%. Not bad. That's a fairly big yield. Okay, there's a couple of practice questions here. I'm going to go through one of them with you, and I recommend doing number 2 just on the side, and you can check your answer here. Impure nickel can be purified by first reacting it with carbon monoxide. Calculate the theoretical yield of nickel carbonyl, or NiCO4, in this reaction if we have 23.5 grams of nickel and we have excess carbon monoxide, so as much carbon monoxide as we need to react all that nickel. And then lastly, calculate the percentage yield if 61.0 grams of nickel carbonyl is actually collected. So that's our actual yield, or experimental. So I chose to do this on a separate piece of paper. If you want, you may want to squeeze it in this area here, but it tends to be messy when I do that, so I just did it over here. So here's the setup. Nickel plus 4 carbon monoxides yielding 1 nickel carbonyl. We're told that we had 23.5 grams of nickel. We have excess carbon monoxide. I think it was carbon monoxide anyway. Yeah, it was. And what we actually get is 61.0 Gs of nickel carbonyl. So what we have to do is figure out what should we have got for nickel carbonyl. So of course that involves 3 steps. Changing grams to moles, using the mole ratio to go from moles of nickel to moles of nickel carbonyl, and then going and changing that into grams. So starting off with that, grams to moles, the molar mass of nickel is 58.69 grams. So we arrange it like this, so grams cancel, and I'm left with moles of nickel. And of course, looking at the equation, 1 mole of nickel makes 1 mole of nickel carbonyl. So 1 mole of nickel makes 1 mole of nickel carbonyl. Even though it's a 1-to-1 step and it doesn't change anything, you should show it so that you can cancel off moles of nickel and end up with moles of what you need in terms of product. And then to go from moles to gram, we need the molar mass of nickel carbonyl, and I've worked that out down here. 1 nickel, 4 carbons, 4 oxygens, as you can see, 107.7 grams per mole. So the last step there, multiplied by the molar mass, and we get, when all is said and done, 68.4 grams of nickel carbonyl is what we get by using the equation, the original amount of reactant. That's our theoretical yield. But experimentally, our actual yield is 61.0 grams. So you can see we got a little bit less than what we theoretically could have or should have. So B, figuring out the percentage yield, actual yield divided by theoretical yield times 100. So 61.0 divided by 68.4 times 100, and it works out to be 89.2%, which is fairly high. Okay, so looking back here, the summary, the theoretical yield is the quantity of product as predicted by the stoichiometry of the chemical equation. The actual yield is the actual quantity of the product collected during the experiment. The actual yield is usually less than the theoretical yield due to material losses, the nature of reaction, impurities, competing side reactions, etc. And the percentage yield of the reaction is the ratio expressed as a percentage of actual yield over theoretical yield. And it has no units, it's just simply a percent. Okay, questions I want you to do here are 1, 2, and 3. Some qualitative questions there. And then 6, 8, 9, and 10. Okay, so that will mark the last assignment, 7.5% yield, just those questions there. Okay, we'll see you again.